welcome. And for those who don't know me, my name's Paul Williamson from ARM. Who's heard of ARM? Okay, most of the room. Okay, good. I won't spend, that saves me the minutes I've lost on the presentation to explain who we are. But, IPO'd over a year ago now, 30-year-old business. In its lifetime, our partners have shipped about 300 billion devices. Our run rate's about 30 billion a year, and I run the IoT division, so it covers a pretty broad range of products, about 20 billion devices a year, 6 billion of which are tiny little smart cards and payment systems, through to really advanced vision-based robotic systems. So a pretty huge range of different devices that my team define the technology for. Now, the world has been changing, and thankfully, the other groups have already, speakers today, have already sort of accentuated some of this story, but we've been on a journey with compute from embedded through to the addition of connectivity, which opened up the ability to share this data across devices, to an emerging world of AI, and that's changed what's needed for compute. Now, what my team work on typically takes at least 5 years till it's appearing in the market. So the technology my team are defining today goes to our fantastic silicon partners like Scott, and they put that into devices that we then need to make available to developers for about 5 years in the future. So we're constantly scanning the horizon of what compute needs will exist in the world in 10 years' time. And as mentioned earlier, one of the analogies I like to give is this sort of human body example. I'm massively grateful for the fact that my body doesn't rely on my brain to process everything. If I was in that situation, as soon as I got on stage to talk to all of you, if I had to think about making my heart beat and my chest breathe at the same time, it would be a pretty short presentation before I passed out. Similarly, if when I come downstairs in the morning, I trod on a Lego brick and had to use my brain to process that, I'd have very sore feet. You know, that instant reaction you get that is localized, that low latency response, is what is needed for my body to function. And the IoT and the AI connected world is going to be just the same. We talked about the cost of sending it to the cloud, but you've got these other factors like performance and latency that are going to drive AI to the edge in a huge range of applications. So we've been working on this for a while. We introduced Cortex-M, and we heard from Scott about processors like the Cortex-M4. It's actually quite an old design by today's standards, but it provides really efficient 32-bit embedded compute. About 5, 6, 7 years ago, we started to introduce enhanced security, and that was driven by that growth of connectivity, the need to connect devices with complex communication stacks and being able to secure data. So it brought in this trust zone for Cortex-M embedded devices, which really unlocked the ability to securely connect global devices. And now we're in this edge AI period, and we've introduced 2 key technologies to address that. One is the latest range of our microcontrollers that have brought in technologies that accelerate vector performance within the CPU itself. And then an addition of dedicated embedded neural processors to accelerate algorithms when you really want to hit higher frame rates or larger data sets with AI compute capability. I want to touch on helium because I think it's somewhat the unsung hero. Scott mentioned a little bit about sort of the M55 coming up and whether people really need a dedicated MPU. Helium built into the latest range of Cortex-M processors like the M55 or the M85, and I'll give some examples later, has these additional instructions that give you this up to 128-bit vector size operations and the ability to run multiple in parallel with lower bit precision. And that really drives up the level of performance, as I'll show you. And to make use of this, it's all compiler generated. ARM has supported the most popular compilers around the world, and if you recompile your code with LLVM, you'll get a level of auto-vectorization to make use of this on the latest processors without having to fundamentally change the way you develop code. So a really powerful technology to really improve the AI performance that you get with low power embedded devices. But then we've moved beyond that to neural processors. And the latest embedded neural processor, we got into Ethos, our embedded neural processor, quite early for the market. I think the market was still trying to understand, was edge AI going to be real? And am I going to be running AI algorithms on a microprocessor? But this year, we launched our sort of third generation product, our Ethos U85. And thankfully, we were able to predict far enough in advance that transformer networks were going to be a disruptive and large impact to AI processing. So this was built with dedicated hardware optimization for transformer performance. And it's a more scalable design, bringing into embedded microcontrollers up to 4 TOPS. And I know TOPS isn't a great measure, but 4 TOPS of embedded acceleration for neural networks. So that means we end up with this really broad scale of embedded neural acceleration performance from, at the base end, just helium-enabled microcontrollers with M55, M85, through to being able to do a full implementation of Ethos U85, where you've got 2048 Macs executing in parallel, able to give you 4 TOPS of embedded performance in a microcontroller footprint. It's incredibly powerful to have that range, but there's a lot of system things you have to think about when you're using this. The compute scale is there. It's ready for you, and we've got great silicon partners, as I'll show you, who are building novel and innovative systems. But as I'm sure if you're AI developers in the room, you'll know, the memory footprint is as big a part of the problem. So you're going to have to consider, when you're developing your models, not only the compute performance and energy, but what is the memory available to me in this environment, and how does that as well impact the power consumption of the design? So what is the sort of limit of where we're going to see this sort of embedded compute acceleration? Well, we see a couple of thresholds, and memory is one area where it sort of starts to create a limit. So we've gone up only to 4 TOPS of performance in deeply embedded microcontrollers. And that's not because we couldn't go faster. We couldn't do a bigger configuration of an Ethos design. But for today, the limitation when you're getting to that level is more about the memory that you're putting alongside it and the power required and the bandwidth that you need to feed that memory system with to fully utilize 4 TOPS of performance. Starts to break through a threshold where you're no longer in the sort of microwatt performance that Scott talked about. So yes, we can talk bigger. We can certainly go to 20 TOPS, 30 TOPS, 100 TOPS. But then we're talking about a very different system in performance and design terms. And I'll tell you a bit more about those shortly. But I'm going to show you what you can do with just 4 TOPS of performance in the right memory system. So the demo I'm about to sort of screen here is showing you our Ethos U85 on an FPGA. It's not out there in silicon yet. And it's running a small language model. So this is a 15 million parameter model. It's not a huge model. It's trained on tiny stories, and it's running only at 32 megahertz, so a relatively low frequency FPGA implementation. But you can see it's giving you pretty much close to human reading speed, about 7.5, 8 tokens per second generation. That's actually only on a 512 Mac configuration. So if you remember from the previous slide, we can go to 2048. So you're sort of a quarter of your maximum compute capacity. You're already getting to human readable speed of a small language model. So the memory is the bigger question here. With that 15 million parameter model, we're talking about needing maybe something like 320 kilobytes of SRAM for caching or tightly coupled memory for your weights and so on. And then for the overall model, you're needing something like 32 megabytes to store that. So you can see that the memory threshold is the thing that's going to limit this capability in these deeply embedded applications. So we need tools that help developers to understand these trade-offs, and that's why we're so excited to be working with Edge Impulse to provide those and enable developers to really exploit the performance of compute that is coming in silicon. So what happens when you go for these bigger models, and what is the threshold you start to cross? Well, when you get to those higher performance designs, we actually have made Ethos U85, something you can directly couple into a higher performance system. So this image is just to show it plugged into a Cortex-A based processor. Now, a Cortex-A based processor, or a cluster of them, of those CPUs, is typically what you'd find in a higher performance Linux based device. This is something with a DRAM interface and the ability to run Linux, but we're seeing significant interest in deploying these micro NPUs alongside that higher performance compute. And we see it in sort of two different configurations. One is as a sort of small embedded AI subsystem. So today, if you've got your smartphone, there's a low power island in there that is doing your activity monitoring and tracking. If you take that forward, what people are wanting is an AI island, something that can do the AI performant processing as a subsystem within a higher performance system, so that when it's, say, scanning the image of the world, it can decide that low frame rate in the background, is there some event of interest here before I spin up the higher performance system and start applying larger models with bigger data sets to that system? So we're seeing sort of power islanded AI subsystems, which is an exciting evolution. But we're also seeing people want to run, not necessarily a large language model, but offload and accelerate an always-on, relatively high performance, just 4 teraops model directly from an A-class CPU, primarily because they want to operate with high-level languages. They might want virtualization or a container-based system in which to run their AI so that they can upgrade it for one of these many models of the future. So you may have a production line with a bunch of Linux-based systems on there running virtualized that can also make use of a small accelerator for image-based signal processing. So interesting evolution in where we see this going for the future in systems. Now, I mentioned about how we work at those lower layers on the tools to make this simple, and I've already sort of talked about this a little, but we work with the microcontroller to allow you to just take your embedded model, your TF-Lite model, run it through a standard compiler, and then get an output that you can drive through kernels that are optimized with our SimSys neural network libraries and just execute directly in the microcontroller. When you introduce a neural processor, it is a specific and different bit of hardware. And you do have to go through this extra step to make use of that hardware. But we've created our Vela compiler, again, optimized to allow you to take that quantized model and deploy it in an embedded variant of our neural processor. And you can do that within your common embedded tooling environment. So what is the performance level difference between these different classes? So I've baselined this to Cortex-M4 because I think it is a great processor. And I see really powerful applications running on Cortex-M4 today. I gave an example. I'm lucky to sit on the board of Arduino, and we had a partner using just the NICLA which happens to have a Cortex-M4 on it, to do viniculture monitoring for beetle infestation in crops in northern Italy. And they're doing computer vision on a Cortex-M4 at about 1 frame every 5 minutes, because that's all they need to do. But it works beautifully. You've got this little battery-powered device, and it can spot the first beetle to land on the plant and infect the leaf, and they no longer have to mass spray pesticide. They can spot treat in regions where it's happening. So you can do good AI on a very simple processor already today, like the M4. But as you see here, you get significant uplift. So M33 gave an improvement. M7, a higher frequency performance level of that generation. But when we moved to add helium, you can see you're getting a 6 times improvement on a similar frequency basis in the processing capability. And then when you deploy to a dedicated neural processor, those parallel MAC instructions give you a 22x improvement for audio benchmarks. Now, audio mark is a mixture of vector performance for the DSP and filtering and AI neural net performance with matrix mathematics. So you're getting that very impactful uplift. And as Scott said, that isn't necessarily about raw performance advantage. It can be the ability to process and go back to sleep and constrain your power consumption as well. So really powerful optimization. Now, we've worked with Edge Impulse to make sure that access to this capability is plumbed into their tools so that their developers can make full use of it. So you still need your embedded developer flow to be able to sort of sense the data, plumb in your interfaces, and drive your outputs and your decision making, your communication stacks. Your signal conditioning is a really important step. We were talking about this over dinner last night. The more you can do in signal conditioning to extract data before moving to your ML developer flow, the more you can reduce the power consumption that you're using in the high bandwidth compute of an AI algorithm. So there's a lot of benefit from upfront digital signal processing to filter for useful data before you go into that ML path. But as I just saw in a demo outside, which I'm sure they'll repeat for you, the Edge Impulse tools are ensuring that they've got blocks to plumb in to do that pre-filtering, which is great to see. And then we put our tooling into the back end that allows you to compile, validate, and even estimate performance on different target hardware. So I'm just going to run through some examples of this. And we've heard from Scott, the Apollo is an incredible instance of M55, which is really driving that MCU energy efficiency in an implementation. We also have partners out there focused on different applications. Himax, Taiwanese company, really early in doing really interesting things with video type bandwidth. So they're giving you an Ethos U55 with a Cortex M55, plus camera interfaces like MIPI to give you camera processing capability. And Alif, who are out there in the demo area as well, also really stepping that up to the next level with bigger memory systems and capabilities. So some fantastic stuff. And we've already heard demo examples with Renesas taking the M85, which is a really highly clocked helium-based processor for algorithm execution. We're not just focused on AI performance in the deeply embedded environment. If you're using A-class systems and Linux and you're needing these larger memory systems, we're continually driving the introduction of additional operator performance that is going to change the level of AI performance you get in the latest A-class processors as well. So Cortex A73 generation is a sort of common one today, and I'll show some examples, but where we're heading, the upcoming devices that are being shipped today, A720, able to give you a 16 times inference performance improvement, driven by the support for our scalable vector extensions and also functions to support new data types like bfloat 16. So you can get some really significant uplifts just by moving to newer A-class based processor design. And in that A-class world, there's a lot of development environments out there as well that you can make use of. So clearly, Raspberry Pi, perhaps the most well-known today, they're on an A76 processor, so not getting that very latest performance uplift, but a range of companies like MediaTek are now bringing higher performance, more modern devices into the market. On back there, we even have partners like NXP with their IMX, where they're mixing different classes of processor to allow you to have that low power island as well as that high performance system. And the demo actually that Edge Impulse partnered on with them that allows you to take an NVIDIA Tau model and deploy it directly into the Ethos-based accelerator running in that IMX platform is a really powerful development platform. Now, if you're interested in understanding who's using ARM technology and what tools and what capabilities they bring to the equation, we've got a partner ecosystem catalog you can go and look into. And there's expertise there as well in consulting to provide support with your development process as well. But Edge Impulse, as you can see, a key partner within that. So there you go, a whistle-stop tour of what's happening in the compute side, where to look for the upcoming silicon platforms that could be your next platform for development to use with Edge Impulse, and all of that built on where we're looking for the next 5 to 10 years in ARM. I hope that's useful. With that, enjoy your break. Thank you very much.